Making sure all of that is working. Good afternoon. It is Friday. It is Q&A Friday to be exact. And looks like everything is online. I believe we're up and running. So looking at the chat, if you're out there, let me know you hear me. And we are ready to do another great Q&A Friday. I was just monitoring NFPA 70E, so they haven't broken for lunch, but we did because it is time to take a look at some questions that came in. And I'll tell you what, we have a lot of good questions, so I'm going to get right into it. Welcome, everybody out there in YouTube land, Facebook land, LinkedIn land, Instagram land, Twitter land. I think that's everybody. So I got Yellow Duck running right now, so that's a good thing. All right, so I'm just going to double check and make sure that we are golden. Yes, we are. Okay, well, we are going to take a look at some questions. Let's and like I say, I got quite a few actually. We're gonna going back in time. Have any other studies done that you could share, please? That was on the fault current. So we had some questions around. I would love to understand more when to use the correct formula at each stage, when to use cosine, sine, or inverse tangent, polar or rectangular along the way. If not a study, could you recommend some reading that would assist me better, please? So it looks like we have an individual who's looking for a study. Hey, Nihad El Sharif in the house. Thank you, sir. I appreciate the feedback that you can hear me. So one individual is looking to understand some more studies, and they're referencing my fault current calculations lab. I would, and they're asking when to use cosine and sine or inverse tangent and polar or rectangular along the way. And I will do, I think I have a video that talks about complex numbers. So what you're interested in understanding more of when you start talking about cosine, sine, inverse tangent, polar versus rectangular formats, you're talking complex numbers, dealing with, again, the power triangle, right? And there are various references that I use to help me with that, to help me understand that. One of those references was the book that I reviewed yesterday. It was Blue Kreutzig or whatever that is. Yeah, thanks, James, or James Smith. Yeah, that other, the one that had all of my reference materials, that's the one you're going to want to look at, because I talk about all of those with all the different formulas. But I think it might be a good idea at one point, James, I don't know what you think, but it might be a good idea just to go over some complex numbers, which I think I did it, but it's always good to redo stuff. So keep an eye out, and you might see that one. Okay, how about, can cable limiters ever be used to accommodate? I thought I answered this one. Never seen it done. Cable limiters to accommodate lower power. I think I answered that one. Hey, Felix, good to see you. I believe I answered that one. I'm double dipping here, so I might not have copied the last Q&A on this one. Okay, pad mount transformers connected to a multi-megawatt inverter. Often there's need for a small amount of 120 volt power, and this need may be met. Mini power centers. This is JW. The mini power centers normally have interrupting ratings on their main breaker that are too low for the fault current. The large transformer may be able to deliver. Sometimes current limiting fuses are needed ahead of the mini power center. Yeah, so he's speaking to the video that was on short circuit calculations and equipment evaluations. And remember, yeah, JW, I think that was answered last week. So I just forgot to put the link to video on there. I'll have to do that. power systems engineering, and I answered that one. That's why we did the video on Tuesday. So Navneet Guard says, if transformer have REF protection, do we need to provide line differential protection also? And if so, and if yes, then why? REF protection, JW, if you're out there, buddy, REF protection on a transformer, REF. I don't know what REF, REF protection on a transformer. Restricted earth fault protection. Here's my thought process. We know what the Article 450 has the requirements for transformer protection. We have primary and we have secondary, and it tells us when we can do primary only and when we need primary and secondary protection. And there's other references in there as well. So if you have a panel board on the secondary, you might have to have secondary protection to provide the protection for the panel board based on Article 408. But Navneet, I would say there's no requirements in the National Electrical Code that tells you need to do differential protection on transformers. If you're applying things like differential protection and those additional levels of protection, you're doing that because of your investment, in my opinion, your investment in the transformer. Right? We're not going to do things like differential for control power transformers, but we will probably do that for very large transformers that you'd paid a ton of money for. So, because it provides an additional level of protection, in my opinion, over and above what's required by the code. So, hey, Gustavo, good to see you, buddy. So that's my guess is, Navneet, that if you're, I'm not familiar with any requirements in 450 that require differential protection. So I would say if you're doing differential, again, it's because you're going above and beyond. All right, so how about JW? You're on deck, brother. You're on deck. I failed to understand why in 145 I'm talking short circuit current calculations and equipment evaluations. I failed to understand why at 145.15 it was said that you should consider the impedance based on the transformer's rating if no fans. Okay, I'm going to read your whole question. If no fans are used, rather than the higher rating if the fans are used. I had understood it that the %Z basically is what % of the transformer's available short circuit current it is able to deliver at its rated load. So if you take rated kVA and divide that by %Z, then you get short circuit kVA. I fail to understand the statement that %Z should be the same at both kVA levels. To me, %Z, the transformer is shorted, changes at the higher kVA value. It would seem it would have to be a manufacturer standard to mark the %Z at the lower kVA value and not something of electrical theory that %Z stays the same. Okay. Restricted earth fault is basically, I've heard the term. Okay, so JW, so here's what, man, I'd have to look at my, I'd have to look at the standards too, but what if you recall the nameplate, let me see if I have that PowerPoint presentation. The title of that was Short Circuit Current Calculations and Equipment Evaluation, and I believe that video was done. I gotta look at the date of when Whoops, sorry about that. The date of that was March 30th of 2020, so that was last year. Okay, so let me just do find my, if I can find my March, there it is. There's my March 30th presentation. Gosh, I love this stuff. Look at that. You can't, this is just too good when you're organized. You know what I'm saying? So let me find that, that slide. which was the picture of a nameplate. And it was the medium voltage transformer. Where's it at? All right. Come on. To find the nameplate for the medium voltage transformer. I think it was later in the presentation. And if my memory serves me correctly, which nowadays my memory does not serve me as correctly as it used to, because I am apparently getting a little older these days. All right, so I'm just going to hit delete there, and I'm going to do PowerPoint. I think. Yeah. Okay. So this was the nameplate that we were looking at, and if you'll notice, I have AAFA, which has 2 different kVA ratings. It's because I'm adding fans. So what you have going on is you are putting fans on the transformer to control what happens with the heat, right? So I'm able to push more kVA through this transformer because I am cooling it with these external methods to get it cooler, so I can handle more load. But remember that the percent impedance is a value that is generated not because of the cooling of the external cooling. That value is based upon the physics of the iron core and how we do the short circuit test and open circuit test and all that other good stuff, right? So we're establishing the key parameters for the performance of this equipment when a short circuit occurs, right? So, and you're passing through it. And remember, if you think about our calculations, think about how we represent different equipment. Say a motor as an example, because they're very similar, right? If you think about what a motor is, I could argue it's very similar to a transformer. I mean, you have iron, you have separate, you have a rotor which has windings on it. You have a stator which has windings on it, and you're transferring energy from the rotor to the stator, or the stator to the rotor. It's rotor to the stator if it's a generator, or stator to the rotor if you're a motor. So all of these, I believe, in my opinion, even if you look at the diagrams for a motor and how we model a motor and a transformer, they're very similar, very similar. Now, what do we do for the impedance of a motor? We have different impedance values depending upon the duration of the fault current, whether it be the first cycle or longer. So we will change the impedance of the motor based upon how many cycles of current, because we know that that is a changing impedance. With regard to the transformer, we're looking at the short circuit impedance through that transformer, what impedance it provides to the system. Fans aren't going to make a difference. The fans are there to cool it over a time period to get more kVA out of it, but it doesn't change the physics of the transformer itself, because we're looking at what? A cycle. And when we do our calculations, we're looking at a quarter cycle or the first half cycle, right? And that's where you get the most impedance. And whether or not I have fans on it doesn't make a difference. I'm not changing the physics of that. And I don't make that up. So, and I got that from, let me see if I have it in my notes, because the impedance of that transformer either came out of the red book or the standard itself. And I would have to look up my reference on that one. Oh, so he says, I understand the fans make no difference. What he's asking is, how do we conclude, drum roll please, How do we conclude that we use the lower that the percent Z is based on the lower kVA marking? Because that's how it's listed and tested. So in fact, let me see if I have the transformer standards. So if I look at the standards for development of the percent impedance for a transformer, then I can't remember which, I don't know if it's C57. Let me just double check. I got to look at what my standards are. C57 is instrument transformers, C57.13. IEEE, let me try C37. That's breakers. C37 is going to be breakers. Yeah. You know what I'll do, JW, and I understand. That's a good question, which I will put that, and I usually put it in my notes of my PowerPoints, but for some reason, I did not put it in there. But I will add that, and we'll include that. I don't know why I did not put it in there, but I will see if I can add that. Whoops, I had the wrong logo on there. Sorry about that. Yeah, so I'll double check that standard, and I will try to get that for you. Okay, all right. Where's my numbers? Where's my not my numbers? Where's my questions? Short circuit. Where is my, gosh darn it, there it is. Oof. All right, that's the 145.15. And again, JW, I will follow suit and find that reference and get the exact language from the standards so that we keep us all on the same page. I'm just going to make a quick note. Transformer XFMR percent Z lower FLA. All right, no fans. Okay. Should they be using the term? So the next one is 240.87 and 2 versus 240, and this is JW again. Let's take a look. Shouldn't they be using, I'm going to move this over here. Shouldn't they be using the term long time pickup at both 240.6 because, B and C and 240 long time pickup. Let's take a look at 240. Let's take a look at 240.87. And this video there was confusion going. I had some individuals who were saying, look, because I locked the cover and it is no longer a 1200 amp breaker, it's a 1000 amp circuit breaker, I no longer have to do 240.87. And what we showed was that's not the case because it can be adjusted to a higher rating. So what we say in 240.87 is where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1200 amps or higher. And that's the same language that's in 230.95. It's similar. It's almost the same. It might be exactly the same. I don't know. I'd have to take a look at 230.95, but we got the language for 240.87 from 230.95 because we didn't want to create something that that people would scratch their head and go, what are you talking about? So we took that language. Now to JW's point, let's take a look at 240.6. And I haven't read the rest of your question because I just want to read this one first because little chunks, that's where we're at, little chunks. 240.6 says standard ampere ratings. And you're saying, shouldn't they use the long time pickup? The standard ampere rating for fuses and inverse time circuit breakers shall be considered shown in 240.6a. And then you have the adjustable trip because the long time pickup, and you mentioned B and C. I just read A, but B and C is when you have an adjustable trip. The rating of the adjustable trip circuit breakers having external means for adjusting the current setting. And it does say long time pickup setting. So, shouldn't they be using the term long time pickup? And they do, JW. They say long time pickup setting So I would agree with you, and it is in there in a paren. So they're relating the rating with. There you go. Thank you. Hair looks good. They're relating the rating with the long time pickup with the rating of the adjustable trip breaker. So I also think this misinterpretation might be avoided if people remember that the fault current is usually nearly the same for an instant, regardless of the circuit breaker size. That is exactly right. Yes, and that's the point. You nailed it right on the head, and that's a good way to look at it, JW. It's the impedance of the source that matters. I think when coming up with something to put in the code, they assumed the breakers of a certain size are more likely to be connected to the higher capacity transformers. Since in many installations, transformer size can depend on the utility, it was decided to make the rule based on the breaker size rather than creating a bunch of different rules that might change based on who owned the transformer. Yeah, so remember 24087 and 24067 apply to any breaker or fuse, AC or DC, but not medium voltage, 1,000 volts and less, whether it's a service or a feeder, wherever it's at in the power distribution system. So the determination of when you needed this requirement for arc flash reduction is driven off the size of the equipment. But I would agree, JW, that in reality, the size of the overcurrent device really doesn't matter. It's the relationship between the arcing current and the trip curve. So I could have a 600 amp circuit breaker that I have a very high incident energy downstream of that breaker because of where the arcing current lies in relationship to the clearing time. And if I'm selectively coordinating my system, that 600 amp circuit breaker is going to be definitely it's not going to have the arcing current in the instantaneous region on that breaker because I know that I'm selectively coordinated. So I'm looking and comparing the overcurrent devices with their three-phase bolted fault current value. And I know that's, if it is in the instantaneous region, it's just barely in the instantaneous region based upon the circuit breaker selective coordination tables. So I know my arcing currents are going to be in the long time region or short time delay regions of those breakers, regardless of the size of the overcurrent device. So, but this is a start because we know that these larger overcurrent devices present even more of a challenge based on where they're at in the power distribution system. If you're at 1,000 amps or greater, or 1,200 amps or greater, you are up closer in the power distribution system, and there's even more distance between you and the downstream. Since in many installations, transformer size, okay, so we already read that one. Hopefully that helps, and I agree with your point. JW says, will you be at the Northwest Section Joint Section meeting? Thinking of going? So, I'm not planning to be there. I would love to be there, but I have so many. I'm on 70B, which is in cycle. I'm on the National Electrical Code, which is in cycle, and 1078 and 1078, those first draft meetings are coming up, and I'm in cycle. So I've got a lot of stuff going on, and I just can't do it. So I'm not going to be there, JW. I would still say you should go. That looks like it's going to be a good meeting. He says he's seen Eaton fused bolted pressure switches that actually say you have to use 90 degree C rated conductor, but size the ampacity at 75 degree C ampacity max. You could not use a 60 or 75 degree C conductor in this equipment. This goes to the concept of the conductors absorbing some of the heat. Temperature may be more than 75 degrees C. Yeah, so, I think the point of this discussion, this was the 80% versus 100%, and the sizing of the circuit, the conductor that you're landing on the overcurrent device, and I don't know, JW, if it's directly related to that it would trip the overcurrent device, or that it would degrade the equipment because of the added temperature. So I think it might be a little bit of both. Robert from Omaha in the house. How do you handle the no plan review because it costs money and not required by the state? Is it critical to be done? Robert is commenting on the live session that we did with the IAEI, with the IAEI live event, which Tuesday we're going to hear from Larry Ayer. So we're going to be online this Tuesday coming up at 12 o'clock Eastern for 1 hour. We're going to have Larry Ayer, Correlated Committee Chair. He's going to be talking about the stuff that's going on right now in between the first draft and second draft. So you're going to want to join on that one. And don't forget to subscribe to the IAEI's YouTube site. We're growing that channel. You are going to want to be a part of that. Come along for the ride, and it's free. The plan review, in my opinion, is critical, and it can save you money because it could yield a successful site field evaluation, or not field evaluation, a field inspection. So when your inspector goes out there and he starts looking, or she starts looking at the installation, you should have all the details covered in plan review if you've done that. And if it's not required, and even if the state doesn't do a plan review, you can still get one done separate from that. And I know a lot of consulting firms that I guess I would be in error saying a lot of I know a handful of consulting firms, but I don't believe that they are unique, that employ electrical inspectors who either were past electrical inspectors and are doing consulting work where they look at plans, or they'll go to the site and do a site inspection just to avoid those red tags and make sure that the projects all go on cue. So I think it's important. Didn't and won't have time for this one, but here's a suggestion. We draft one of our own to run for Congress to pass a law to give us all this library for free. Oh, I remember that one. And then Quinn Coates, thanks for the comment on for the quick overview. That was on selective coordination tables and tricks. Got a process server to dump your plans at City Hall so they can say they at least had a chance to review them. And JW saying that he thinks that it should be in 24087, so it's completely understood. And you know what, JW, that's not a bad idea. It's not a bad idea for the long time pickup. All right, so in some cases, like Puerto Rico, the where the utility is very weak, so as to cause crazy voltage drops due to inrush current, you may not be able to rely on the utility being able to supply certain amount of fault current. Yeah, you're absolutely right. And what we found, I would say it doesn't have to be like we have done some studies and looked at available fault currents, and the reason we did that was for 210.12 AFCIs, and we found that the available fault currents vary considerably across the country. And right here in my backyard in West Virginia, my last house had a very low available fault current. I think the transformer was and it was hard to tell. I never really called the utility. I just measured it at the house, and it was like around 400 or 500 amps. And I think the transformer was on a pole outside down the road. So, but yeah, I agree with you. You just never know. Eaton's double door safety disconnect switches don't say in the literature. All right, here we go. And I sent the question down to Nick Cluse, who is the product line manager. Wait, what happened? Yep. Eaton's double door safety disconnect switches don't say in the literature if they can be considered suitable for use as service equipment. Also, one challenge I think may exist with specifying them just based off of seeing a photo is they are taller, making one have to adjust to not exceed the the 6 point. So the product that he is talking, that JW is talking about, is Eaton double door safety switch. Up. I gotta fix something. Hold on. Gotta take that out and put that in. Just gotta fix the Q&A Friday. So Eaton introduces the double door safety switch. This is the product that JW is. I absolutely love this product. I think it's a great idea. And here it is. Let me get me out of the picture. All right, so this one here is the double door safety switch, and the handle is up on the top part of the enclosure. It is a little bit taller. Let's just take a look at the switch portfolio. Got all of my information in there. Oh, I agree. Okay, here we go. Here's the switch portfolio, and then that's the portfolio. I want download the graphics, frequently asked questions, double door, download the brochure. I don't want the brochure. Do I want the brochure? I was looking for the dimensions. Regardless of the dimensions. It is a taller JW. It is a taller enclosure. You would mount it on the wall. I mean, the fuses don't have to be at eye level. The fuses can be down lower and the disconnect. So you got to make sure that handle is at the right height. But again, it depends on the space on the wall, as with any disconnect switch. But what it does is it separates. You can isolate, and the options that come with that. You can put the presence of voltage indicators in the top. You can put a window in the top so you can visibly see the disconnect of the blades, and that establishes an electrically safe work condition in the bottom cabinet where you are replacing fuses. Or if you're doing any monitoring in that fuse cabinet, it at least separates that. It brings the lead out. We can bring the leads out. Like if you want to do presence of voltage, you don't have to do the monitoring down on the fuses. You can look at that presence of voltage, even when you open it, to indicate the line and load side of the disconnect. So there's it's a very absolutely a innovative. If you can innovate something that is as simple as a disconnect switch, you're really doing a good job. So in any case, you do have to consider the height. I don't know. I haven't had anybody complain that they would not be able to provide that, meet all of the different restrictions. Let's go up. They should put some arcing current calculation examples into the annexes for the NEC. That's a. So here's JW. Here's my thoughts on that. I think the first thing we have to do is probably put a definition of what an arcing current is. We have a definition for available fault current, but we don't have a definition for the available arcing current. And I would argue that you'll want a minimum arcing current that you need to consider, but we don't say that anywhere in the code. I don't necessarily disagree with you about arcing current examples in the annex, but I think the first thing we really need to do in the NEC is define what is the arcing current. What are your references to calculate it? Now, Bussmann, Eaton has an arcing current calculator, and I think it is, you've got to have your fingers on the right keys when your arcing current calculator, and I think it's we have two of them out there. One is based upon the 2002 version of 1584 energy calculator. Bussmann. I can't remember. I gotta remember what it's called. Bussmann arcing current. I think it's arc.bussmann.com is the arc.bussmann.com. Let's take a look at that one. Yeah, arc.bussmann.com. Basically, this is an arc reduction calculator. You put in the information associated with the equipment. And I have some information here. So 25 is a shallow, deep, low voltage MCC or panel board. 13 is your cable junction box. 32 millimeters is your low voltage switchgear. So if I had a panel board, I would put 25. Electrical configuration, this will be your VCBB, VCB, or HCB. I only put those three in there. And then you have the voltage that you're at. So if we say 40 volts, what's your fault current? So if we said, I don't know, 72, and it's in kiloamps, so 72 kiloamps, fuse ampere rating, I don't know, say we pick a 1200 amp fuse and we say calculate. It tells us based upon, these values are based upon these two values are based upon the 2018 version of IEEE 1584. You have a maximum and minimum based on all the parameters that you just put in. And then what this does is an evaluation with the fuse to see, do you have the 0.07 second clearing that 240.67 requires? If your minimum arcing current has a clearing time of 0.07 seconds or faster, then you don't need an arc reduction technology. And this will tell you for those fuse sizes, whether or not you need or do not need an arc reduction technology. So, but I agree with you, JW, and the challenge there again is the amount of the equations that you would need to do that. All right, let's take a look at another question. Hopefully, as we move on. Okay, when is an example where in reality the X to R ratio is so low as to be of a concern? Seems like they go pretty low in tests, so I am wondering what installations are actually so low as to need any adjustments. Also, how does the X to R ratio of the utility power source differ in impact from the X to R ratio caused by the power factor of your facility? All right, so what he's asking is, and it's not that the X to R is low. I believe the X to R ratio has to be higher. Because the we tested at, hold on, let's grab I have a presentation here. So let me open up my PowerPoint that talks about the X to R ratio, because what this is dealing with, so let's just do this. So this is my short circuit presentation. Okay, and I know in here somewhere, hold on, let me find the right slide. It's down further and it's where, here we go, right here. Okay. So, and what the X to R ratio is doing for us is giving us that DC offset, that asymmetrical first half cycle. So the larger the X to R ratio, the greater the initial peak of the waveform. And typical ratios are from 5 to 6 to 1, up to much greater than 10 to 1. And what we test our breakers for is, I think, 6 is worse. And what we're doing basically is we're showing that difference between the two waveforms, between V and I. And I do an example. So what is the X to R ratio of a circuit with an 80% power factor? You know your inverse tangent, X to R, so and cosine, inverse tangent of X over R is your theta. So tan theta is equal to X over R. So the tangent of 0.8 power factor. So R cosine of theta is 0.8. You take the inverse cosine of 0.8, and that gives you your angle, and then you take your tangent of your angle, and that tells you that an 80% power factor is 0.75 X to R ratio. So this table gives us the X to R ratio for at 80% all the way down to 5%. And it's when the power factor goes too low. And I think that's what you were talking about when you have such a low power factor. And I believe it's right around six X to R ratio of 6 or better. Right, 6 or less is where we cap out. I'm almost positive. And what this does is it shows you the phase angles. So, and the difference. So this is a 90% power factor. Your delay between voltage and current is pretty close. So then your angle was what, 25.84 degrees. And then as you go to 80%, now you have a better separation between your voltage and current. It's that lagging factor. Then as your X to R ratio increases, you look at your X to R is 1.33 now, it's 1.73, it's 3.87, it's 6.59. And if you look at your let me get my laser pointer. If you look at this is your voltage and this is your current. As your voltage is coming down to cross zero, your current is peaking. So my voltage is approaching zero, but my current is approaching its maximum value. It can be very hard to interrupt that current. So as your X to R ratio increases, your power factor is decreasing. You have more X in the picture. So what's happening is gotta go to the next slide, is you're separating your voltages and your currents. So so an X to R ratio of 6.6 or less is good. So if you go above 6.6, then you run into a challenge with the circuit breaker. Now, your question, when in real life might you have a power factor that's low or a high X? I would say that it is probably when you're on the secondary of a transformer, and you have a short run of conductor, and it would have to have let's just do it real quick. Hold on, I'm gonna bring up SKM. Let's bring up SKM, and I have an example that I was using with regard to trying to help people understand the what do you call it? The new requirement in Article 230 about separating the disconnect. So here's a transformer. What I have here is I have a utility, and let's take a look at what my utility is. My utility X to R is 8. I think if you there was a reference for a typical utility X to R ratio. Hold on. Examples. Let me just because in this generators, utilities. Let's take a look at utilities. There's my power triangle. There's my use. Okay, utilities. Fault contributor utilities. All right, utilities. Okay, blah 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 blah. All right, so just looking to see what the X to R ratio. I know that they provide an X to R ratio. I could have swore that I had some information in this slide deck that was related to the X to R ratio. So hold on. Maybe I don't. Thought I did. see if it's in the notes. It's not there. Not sure where it's at, but so there's some IEEE standards that'll give you some ballpark figures, and 8 is not a unrealistic number from a utility perspective. So 8's not a bad number. Then I have a conductor. I have the primary, and I put a conductor length in there just primarily to satisfy SKM. And I have the transformer. I have 5.75% impedance on a 4160 to 480 volt transformer, and I have a conductor run of how many feet? Conductor run of how many feet? 15 foot. So I have 15 foot on the secondary of that transformer. It may or may not be realistic. Now, if I used busway or other, I mean, that depends upon the equipment that you're using. So there's my available fault current. I'm just going to run this again, balanced short circuit study. I'm doing an ANSI. I'm using the A fault. And I hit close, and I'm going to go to document and reports, text. And we're going to take a look at what the, just for this small example, short circuit, open. What bus number is this? This is bus 4. Bus 4 is down here. So let's scroll down. And what you'll see is that the X to R ratios will be in these reports. So here's my X to R. So bus 4 has 37,916 three-phase duty. And my X to R ratio is 7.39. Okay, so now let's do this. 7.39, that would be greater than the 6.6, right? So that would be a little bit of a cause of concern. Let's take this from 15 to say 30 feet. And let's rerun it. Control A, run, forced run. And let's go back to our report. I got to close that, and I got to go to document. Document, reports, text, short circuit. And I'm looking for bus 4. There's bus 8. Bus 4, I gotta go down. Sorry, hold on. X to R is now at bus 4, 6.89. So the more conductor you start adding on the secondary of a transformer will bring your X to R ratio. And why? Because there's a lot of resistance inside of a conductor. So my answer to you, JW, is in real life, where you might see a concern would be on the secondary of a transformer with a short conductor run. And then you have to take into consideration the entire system. So again, I'm only showing a very small portion of this. I don't have any motors in parallel with any of this stuff. So where I've seen it, where it would raise an eyebrow, a little bit of a concern would be on the secondary of a transformer. So hopefully that helps answer that one. I never really considered short circuit current ratings for every small piece of equipment before, and don't think I'm alone. In cases of many pieces of small equipment, it happens to have been listed and made for a typical installation, so there's normally no issues. However, and this is talking about short circuit current rating, the 15-minute tech talk I did, it would help the installation community be more aware if there was more standardizing of things and putting it into tables in the NEC or something. We can't afford to make people have to buy standard upon standard and publication upon publications, even fundraising. So here's the thing. One thing I would say, if you're dealing with a small piece of equipment, you've got to look at where you're at in the circuit. If I'm think about, 10K is like a minimum requirement for a lot of things. 5K might be a minimum requirement for certain types of equipment, appliances, etc. But the conductor that you're on the tail end of will, if it's a small conductor, adds a lot of impedance and it really knocks down the fault current. the challenges that I've seen are not necessarily in small equipment. Your larger HVAC systems and things of that nature are where your challenges are. Now, having said that, I've seen some GFCI receptacles being misapplied very close to service entrance equipment, and the available fault currents are greater than 5K or 2K. If you understand the ratings of the GFCI receptacles, components like that are very easy to misapply, and some of those you just can't throw a fuse in front of. And I would argue that even if you had a 10K GFCI receptacle, it was tested and it achieved its 10K short circuit current rating when you have a fuse in front of it, and you rarely see any of those installed downstream of a fuse. So the whole aspect of short circuit current ratings and evaluation with a fault current is challenging. I would agree. And the code's trying to help raise the awareness of that. But to your point, it doesn't make life easy. So we should be doing an evaluation based upon where you're at in the power distribution system. Series ratings, you said another reason we need a PE to be involved in series ratings per 240.86a. 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 I just want to read it just so everybody's out there and know what we're talking about. 240.86 is series ratings selecting under. So there will be different circuit breaker manufacturers. Be mindful that I can't engineer series ratings when I'm dealing with molded case circuit breakers between, say, two manufacturers. I can't take my circuit breaker and say it's going to protect another circuit breaker. If you do a series rating pair, they're going to be tested together, and I'm testing with my breakers, not my competitors' breakers, because I have no control over any of the changes that they make. There's no such thing as an umbrella circuit breaker like you have with umbrella fuses. But you can engineer series ratings when you're dealing with some static equipment like busway and other things like that. So yes, and you do need to be qualified. A citizen of our world says, 10 hours ago, the way I learned it, I would have interpreted 1 minute and 27 seconds. This is in the circuit breaker selective coordination tables to mean the 20 amp breaker will trip first as it is farther to the left on the timeline, and the instantaneous regions of these breakers don't overlap. So as the short circuit current quickly rises towards 1,000 amps, would it not be interrupted before it exceeds 300 amps? Great question. And what a citizen of our world is commenting on is I got to look at when I did this one, because I'll try to bring up those slides. Whoops. Hold on. And that would have been February. Wow, that was an old one. February of 2017. But I know the two curves that you are speaking to. So let me, this is my BAB 20 downstream of the F150, the circuit breaker, not the truck. So I got to go to my power systems analysis, selective coordination, because this is a quiz that I give everybody when I do a selective coordination presentation. I lead with these curves. Do these selectively coordinate? Yes or no? And so what this individual is saying is that his interpretation of these curves, that as the fault current approaches the 10,000 amps, which is way over there to the right on this trip curve, as the fault current approaches 10,000 amps, that the BAB, that red breaker, is going to trip and clear it before the fault current gets to the instantaneous region of the blue breaker. And that is absolutely incorrect. You have to think about what it is you're looking at here. Okay, you've got to think about this curve. What does it represent? Control C, Control V. Okay, so what this curve represents is you look at the time 0.01 seconds is and above. So what you're looking at, if you think about what is what is one cycle of current? How would you represent one cycle of current? That is one cycle of current, right? Move this to this way. So this is one cycle of fault current, which is how much time? 0.016 seconds. And on this time current curve, I'm starting at 0.01. When a fault occurs, it doesn't like ramp up to the magnitude. It goes there really quick. So both of these circuit breakers will see this increased fault current, and it's the first half cycle, which is a doozy, right? What is if this is 0.016, halfway through this right here, halfway through right there is add a text box. This is 0.008 seconds. I'm not even showing that on this curve. So if I had 10,000 amps of three-phase symmetrical bolted fault current value, that's what we calculate, then you add the asymmetrical on top of that, which is this first half cycle, is that, that DC offset that we just talked about based upon the X to R ratio. These two breakers don't have the thought process that, well, as the fault current ramps up, it's instantaneous. And you can't evaluate how these breakers will respond when your fault current is in this instantaneous region. If you're at 10,000 amps and you hit both of these, we have tables where we've tested it, and we know that when these two breakers see a short circuit pass through them that is greater than 1,500 amps, they will both open. We've tested that. And the reason is because of that first half cycle, which is not plotted on this curve. You're starting at 0.01 seconds, which is probably, I would say, about 0.01 seconds is probably somewhere around, I don't know, if this right here is 0.016 and this is 0.008, 0.008 plus 0.004 is what? 0.004, that's 0.012. So this is 0.012. You're probably right around in this area right here with your, on the trip curve, you're showing from here on in time. You're not capturing that first half cycle, definitely not. And a little bit past that. And the first half cycle is what's going to open these two breakers. So, you can only rely, and this is really, it's hard for some people to understand. And what I go back to are the circuit breaker selective coordination tables. For these two breakers, we've tested them and we know any current that they both see above 1500 amps, they will both open. So you cannot rely on these curves when the fault current is into the instantaneous region of both of the breakers. You have to move them. Just because you don't see the foot curves under below 0.01 seconds. And if you went to the BAB breakers, I think we even show those curves. I could try to find them here. Eaton BAB breaker TCC. Let's see if we have those. Time current characteristic curves, molded case. Let me go back. Molded case circuit breaker curves, quick lag. Let's try that. Yeah, there we go. Let's see what we give you. And after this, I gotta go. Yes, we do. Look at that. Okay, here it is, ladies and germs and gentlemen. This is the our quick lag breakers. BAB. Hey, there's our BAB breaker. All of these QB breakers, all this good stuff. And let's take a look at, this is the time current curve, and look, there is 0.01 seconds. There's 0.01 seconds. And there is what the curve looks like below 0.01 seconds. So we do plot the curves below 0.01 seconds, but they cross over below that. So you have an overlap of curves at the higher fault currents. SKM is just cutting them off sooner. So hopefully, see who asked that question. Hopefully a citizen of our world that answers your question. All right. And it's 1 hour. 70E is back up and running, and they've been up and running for about a half an hour. I got to get back on that one. Thanks for watching. Hopefully you got something out of this Q&A Friday, and hopefully you will have a great weekend this weekend, because I know I am. We're going to have a blast. And please stay safe and stay healthy. All right. So take care, everybody. Thanks for joining in. I appreciate you spending your Friday lunch with me. I'm going to sign off. Stay out of trouble, and we'll see you Tuesday on IAEI News Live. Go out to their website. Go out to their YouTube channel. Subscribe to that one, and we're going to have Larry Air, and we're going to be talking about all of the task group work that's going on in between first draft and second draft meetings for the 2023 code cycle. So we will see you. Felix, yes, we will do a 70E class, but 70E, I think today's going to be the last day for the next version of 70E, but we will do maybe a safe work practices series. So Chris Folan, thanks for joining us. Thanks for everybody out there for joining us and live, and stay safe. God bless and take care. So signing off. See you.